Hey everyone, I have a video for you reviewing equations. So we're going to cover the main types of reactions and how to predict products. We're going to cover solutions and the solubility rules, and then we're going to spend some time looking at the complete ion equation and the net ionic equation. So in honors or regular chem, you can't see. There. You should have learned these basic reaction types. In AP Chem, we're actually going to get a little more picky and particular, but for right now, these will do. So here's the main types of reactions. Synthesis, we start with 2 or more reactants, and they form just one big product. Decomposition, we start with 1 reactant, and it breaks down into either elements or smaller compounds. Single replacement, we have an element by itself, so something neutral by itself, and then an ionic compound, and they're going to trade dates. So A is now with C as a product, bonded together as a compound, and B is by itself. Double replacement, we have couple number 1, couple number 2, usually aqueous ionic compounds, and they're going to trade dates. So A is with Y, new ionic compound, X is with B, new ionic compound, and combustion is the last one. So we're going to have a hydrocarbon, so some number of carbon bonded to some number of hydrogen. Sometimes there's also an oxygen in there, don't worry about it. So a hydrocarbon reacts with oxygen, and the products are always carbon dioxide and water. All right, let's work on predicting products. So let's say I give you 2 reactants and we think it's a single replacement reaction. The first step is to determine if that single element is a metal or a nonmetal. If it is a metal, so the left side of the periodic table, you will replace it with the metal in the ionic compound. If it's a nonmetal, you'll replace it with the nonmetal, right? They're trading. We have one single guy, Mr. Steal Your Girl, now we have a new single element. Once you have a new single element, make sure it's not diatomic. It will always be neutral, it won't have a charge, but let's see if it's one of the diatomic elements, and if it is, it needs a little 2 subscript. The diatomic elements I remember by the phrase hike, bro, need, Cliff Bar. So if you're going for a hike, bro, you need to take with you a Cliff Bar. So those 7 are the diatomics. When they are alone by themselves, you need to put a little 2 subscript. And then that new couple that you just made, that's going to be ionic, so make sure it's neutral overall, and we do that by crisscrossing charges. So let's first, I only gave you the names on this guy because I'm evil. Let's actually write the symbols down. So first, aluminum. Well, aluminum is all by itself. It is not one of my hike bro need Cliff Bars. Aluminum is a metal, so when it's by itself, it is a solid. Plus, copper 2 nitrate. So this is an ionic compound, so we need to crisscross. Copper is a transition metal. I don't know the charge of copper unless you tell it to me, which is right here. So 2 plus. And nitrate is one of my polyatomics, NO3, and it has a -1 charge. So what I'm going to do is I'm going to crisscross. This 2 goes down here, this 1 goes here, and I'm left with CuNO3 2. Nitrate is always, whenever anything's with nitrate, it's always soluble. We'll get into that in a little bit, so I'm going to put aqueous. All right, so now we're going to actually predict the products. Well, first step, is the single element, aluminum, a metal or a nonmetal? Aluminum's on the left of that metalloid staircase. It is a metal. That means it's going to trade places with copper. So who's all by himself then? Well, copper just lost its date. So copper is all by itself. Is copper one of my hike bro need Cliff Bars? Nope. So we don't need any number. We just put solid. Even though it's copper 2, it doesn't get a charge, it doesn't get a subscript. All we do for the single element is check to see if it's a diatomic. So now we have a new couple. Aluminum is going to bond with nitrate. I know aluminum will go first because aluminum is always a positive charge. So aluminum is +3, I get that from the periodic table. Nitrate is always -1. We crisscross the new couple, and I get AlNO3, 3. And then we can balance this reaction. I see 3 nitrates on this side. I need 3 over here. Oh, there's 2 over here. So I need to find that common factor between 2 and 3. So let's take a 3 in front here, a 2 in front here. Now I have 2 aluminums on this side. I need 2 over here. I have 3 coppers on this side. I need a 3 over here. Should be good. Double replacement is pretty similar. The difference is we won't have anyone by themselves, so we don't need to check those diatomics. We'll have two new couples. So you're going to trade the metals or trade the nonmetals. I don't care, as long as you end up with a metal and a nonmetal, or a positive charge and a negative charge is a better way to think of it. So let's try this guy. We have sodium, which is always +1, bonded with chlorine. Let's crisscross those. NaCl. We have beryllium, which is in the second column, so +2, and hydroxide, a polyatomic, which is -1. Crisscross those. So now, those are my reactants. They're going to trade dates. So beryllium is now going to be with chlorine, so beryllium and with chlorine. Notice I'm not just going to take the numbers from before. I have a new couple. They have to get to know each other, so they're going to crisscross beryllium with chlorine, so BeCl2, plus my new couple is going to be sodium, which is always +1, with hydroxide, which is always -1. When I crisscross, I get one of each, NaOH. And now we can balance. I see 2 chlorines on this side. I need 2 over here. 2 sodiums. That's 2 hydroxides, so we are good. And last but not least, my personal favorite, let's predict some products for a combustion reaction. First, you have to figure out, do you have a hydrocarbon? So a compound with carbon and hydrogen reacting with oxygen gas. If the answer is yes, then the products will always be CO2 and H2O. Both of these will be gases. A combustion is hot. It's usually a big boom, big explosion. I helped some balancing a little bit, so we'll put an 8 for my carbon, and we'll put a 10 in front of my H2Os, and we should be balanced. You can double check me. But combustion's my favorite because it's the easiest. Products are always CO2 and H2O. So we've seen this already, but I don't think it hurts to go over it one more time. Some vocab on solutions, because a lot of the times when we do reactions, we're going to have solutions that are reacting. So a solvent is whatever is doing the dissolving. A solute is whatever we put in to dissolve. So a lot of times in our class, we have a solute, some sort of powder that we dissolve in a solvent, which is usually water, stir it up, get it to dissolve, and then we have a solution, which is a homogeneous mixture, meaning a mixture of this chemical and of water, and we call that an aqueous solution if water is the solvent, which again, pretty much all of the time in our class, water will be the solvent, so it'll be aqueous solutions, AQ for aqueous. So what happens when a solid dissolves? When I actually put the solid in the water or in the liquid, what actually occurs on the molecular level? Here's what's really going down on the molecular level. So we have some water molecules that look like this. I just did table salt here, so it's NaCl is the same salt that you have in your kitchen. And so we have a nice lattice crystal of sodium and chlorine ions. But what happens when we actually put it in the water is they separate. So we get our Na+, and the negative, the partially negative side of water, which is the oxygen, kind of orients itself towards the positive sodium. And the negative ions, the chlorine in this case, are then surrounded by, I call Mickey Mouse's ears, these guys, the partially positive hydrogens. So essentially what happens is it breaks apart into positive, negative ions, and the water surrounds it in a way that we can't actually see then the salt with our eyes. Water is very, very good at doing this dissolving, especially if it's ionic things, because it's polar. So we know that the oxygen is not sharing electrons equally. It's hogging the electrons. It's hogging the electrons with the hydrogen, which gives it an overall partial negative charge, which makes the hydrogens overall partially positive. So this molecule has a dipole, making it a polar molecule, right? And because we have this partial negative up here and partial positive down here, makes it really good at dissolving things that have positive and negative charges. So from here on out, when an ionic substance dissolves in water, it's going to break apart into cations and anions. Sometimes over our reaction, we put this H2O liquid to indicate that it's dissolving, but usually after a couple of times, I will stop writing that because this aqueous lets us know that something's dissolving. So you can see I have an ionic, there's my positive cation, there's my negative anion. In the compound, the salt, they're actually neutral, right? One of each cancels out. But once we put it in water, we get splitting up happening, positive cation, there's the ammonium ion, and the negative nitrate breaking apart. So what if I had something maybe like this, calcium chloride? Calcium chloride is an ionic solid. If I want to dissolve it in some H2O liquid, that's going to split into its ions. Well, what is this made of? Well, we know it's made of calcium, which will be aqueous. And we know that it's made of chlorine, which will also be aqueous. But let's look at our periodic table to figure out the charges, because when it breaks into the ions, we know it needs to have the charge, right? Water surrounding the charged cation and the charged anion. Well, in my periodic table, calcium is in the second column, and those cations, those metals, have a positive 2 charge. Chlorine is in the second to last column. Those are the halogens, and we know they have a negative 1 charge. So that I get my charges, but something's not adding up, because over here on this side, I see that there are 2 chlorines. So what is this actually breaking into? It's actually splitting up into 2 chlorines and 1 calcium, right? Whereas this guy, we just had 1 of the cation, the ammonium polyatomic, and 1 of the anion, the nitrate polyatomic. In this case, it's breaking down into 3 different things: a calcium ion, a chloride ion, and another chloride ion. And so in an equation, we write it with a big 2 in front. So how are you supposed to know if something will dissolve? Because not everything will dissolve 100% of the time. Some things will, or some things dissolve so well, it might not be 100%, but we consider it very, very close. So these are the solubility rules. If you have an ionic compound with a nitrate, those are soluble, and we don't have any exceptions. If you have the chlorate, same thing. Chloride, I would like you to learn. Those are soluble. Anything bonded with chloride are soluble, meaning they will dissolve unless we have these exceptions: silver, mercury 2, and lead. Again, some negative ions for you to look through, and then here's some cations: sodium, ammonium, and potassium, soluble with no exceptions. The 5 that I starred, I would like you to memorize for our class. I don't think it hurts to memorize the other ones, especially if you're going to be taking AP Chemistry. But the 5 that are starred, I would like you to memorize those rules. The rest we'll get more familiar with as we go. Here's some tricks for you to remember the solubility rules. It's NAG, SAG, so always soluble, no exceptions: nitrates, acetates, and group 1, lithium, sodium, potassium. And then sulfates, ammonium, and group 17 are mostly soluble. There are a couple exceptions, so you'll see in pink we have some exceptions for sulfates in group 17. The exception is PMS, so lead, mercury, and silver. PMS, if those are with any of the sulfates, they are insoluble, meaning they won't dissolve, or group 17, they are insoluble. And then Castro-Bear, so calcium, strontium, barium, those heavy column 2 or group 2 alkaline earth metals with sulfates will be insoluble. They will not dissolve. So pause the video really quick. I'm going to give you 10 seconds, maybe 15 seconds, and I want you to label as soluble or insoluble. So pause. All right, check your answers. Obviously, you may have had to look at the solubility rules for some of these, but we have KNO3 is soluble, BaOH is soluble, BaSO4 is insoluble, meaning it will not dissolve, Na2SO4 is soluble, CaOH2 is slightly soluble, so kind of in between, it won't dissolve 100%, and then Fe2CO33 is insoluble, meaning it will not dissolve. So now that we've had a refresher on solubility rules, we're going to do different types of reactions. So first, what we've been working with in this class are complete balanced equations. So it tells us the overall stoichiometry, and I know you don't know that word, but basically it tells us the overall coefficients, but it doesn't actually tell us who's reacting with who necessarily, like down to the details. We can do a complete ionic equation, which shows all of the ions that are strong electrolytes, so all of the ions that are being dissolved and breaking apart. And the one that we're going to learn about and focus on the most is called the net ionic equation. And this is essentially the main players, who's actually doing the heavy lifting in this reaction. Okay, so it's almost zooming in and just looking at who we care about. There are some elements, compounds, ions that are not involved in the reaction, they're called spectator ions. So they are present, but just like a soccer game, they are not actually playing the game. They are the audience or the spectators in the crowd. So when I go from the regular reaction that we're used to seeing to the complete ionic equation, these are things that we are not going to break apart into ions. So if you see any solids, any liquids, or gases, we are not going to break those down into ions. We just leave them as is. If there's something that says aqueous, but we know it's not soluble based off solubility rules, we will leave that. And then weak acids and weak bases. For now, I will tell you if something is weak, a weak acid or a weak base. We will learn about those more in our acid-base unit. So here's our first example. I'll do this one with you guys. I want you to write the full balanced equation, the complete ion equation, and the net ionic equation. So first, I'm going to put in some kind of symbols. Let's see. I see K bonded with Cl, and we know chlorines are pretty much always soluble unless they are with 3 exceptions, but K is not one of those exceptions. So this is soluble, which means it dissolves in water, aqueous. I see lead nitrate, lead 2 nitrate. Nitrates are always soluble, no matter who they're with, no exceptions. So that means this guy is aqueous. So I have 2 aqueous things mixing together. Now I have a chlorine, and again, chlorine is usually soluble unless it's with 3 exceptions, and it turns out that lead is one of those exceptions. So this is insoluble, meaning it will not dissolve, so we put a solid. And last but not least, we have KNO3. Nitrates are always soluble, doesn't matter who they are with, so this guy is aqueous. Now I'm going to go back and balance. Let's see, I got 2 nitrates on this side, so I need 2 of my nitrate groups over here. That gives me 2 potassiums, so I need 2 potassiums on this side. That makes 2 chlorines, which we already have. So I got 2, 1, 1, 2. So this right here is my complete balanced equation. Now I need my complete ion equation. So this is the equation where we start to split things up, and we only break up things that are aqueous and they follow the solubility rules. So let's start with this first guy here in green. I have KCl, which is aqueous. That means it will dissolve. I see that there are 2 K plus ions, which are aqueous. Right, this 2 goes to both things. Plus 2 chlorine minus aqueous. I'm getting these charges from the periodic table just as a refresher. Now let's go to the next one. This whole thing is aqueous. I have 1 Pb 2 plus aqueous, and that 2 came from over here. Plus, at this 2, I have 2 and then the 1, so really just 2 overall nitrates. So if you have a little subscript outside of the parentheses, that applies to whatever's in the parentheses. So I have 2 of these nitrates that are aqueous. Solids, we leave solids all together. PbCl2, solid, plus. And now we do our last aqueous piece, 2K plus because of this 2, plus 2NO3 minus aqueous. All right, so our next step is to find spectators. Spectator ions are the ones who aren't changing from before and after. So I'm maybe an aqueous ion on the left and an aqueous ion on the right. If we look, I notice maybe we have K plus, right, staying as aqueous, and we have 2 NO3 minuses, 2 NO3 minuses. So for our net ionic equation, those guys that I crossed off are called the spectator ions. They are present for the reaction, but they're not actually doing the heavy lifting. So for our net ionic equation, we write everything, except what we crossed off. So I did not cross off this guy. I did not cross off this guy, and I did not cross off that solid. So there is my full net ionic equation. My spectators were the potassium and the nitrate. All right, I want you to pause the video. Let's see if we got this. I gave you who was aqueous, who was solid, but I would like you to write the complete ionic equation and the net ionic equation. All right, you can check your answers. Hopefully you got something that looks similar to me. Thanks for watching. All right, guys, so in your notes, there are 3 more problems. Equation and practice 1, equation practice 2, and equation practice number 3. I want you to try those in your notes and bring them to classroom day 2. So bring them to class. That's where we're going to start kind of as a check-in. So in this case, I'm telling you what 2 things are going to be reacting. So you have to predict the products. Make sure you remember trade dates, crisscross. You need to tell me if those products are aqueous or solid, and then you need to write the complete ion equation and the net ionic equation. So try those 3, bring them to class, and we will go over the answers together on Wednesday or Thursday.